I need to find the integral of cosine to the sixth times sine of x. I'm not sure exactly how to do this, but I do know that the derivative of cosine is sine. So what I'm going to try is to somehow use a u substitution. I want to think of cosine of x as a function inside of a function, and then use sort of the reverse of the chain rule to try to find an antiderivative here. So I'm going to say, let's let u equal cosine of x. So then this has the integral of u to the sixth times some stuff. I'll leave the sine x here. Dx I'll be able to use to find something in terms of du. So I'll take the derivative of u with respect to x. And then I want to treat du and dx as variables, and then solve for dx. So multiply both sides by dx, and divide by negative sine x. I can plug this in now directly for dx. Negative du over sine x is exactly equal to dx. From here, this sine x in the numerator cancels with sine x in the denominator. So I've got the integral of negative u to the sixth times du, and I can just find the antiderivative using the power rule. I'll leave the negative out in front. Got an arbitrary constant. Then I just need to go back and plug in what u was in terms of x. So I was able to get down to something that looks like it could be the correct answer. I can check my work just by taking the derivative. If I take the derivative of cosine to the seventh of x, I've got to use the chain rule. Chain rule says multiply the derivative of the outside function times the derivative of the inside function, where the outside is u to the seventh. So that's 7u to the sixth times the derivative of the inside, which would be negative sine. 7u to the sixth, the 7 cancels with the 7 on the bottom, so you just have u to the sixth. And then this negative cancels out the other negative. When we took the derivative of cosine, I got negative sine. So we end up with u to the sixth times sine of x, where u is cosine x. That's exactly what we needed. So this works. I want to make it a little more complex though. So this was really easy because sine of x is exactly the derivative, well, almost exactly the derivative of cosine. It's just off by a constant multiple. But I can adjust this a little bit and still handle the antiderivative. This can be applied to a wider family of functions that come up in applications. So I'm going to change sine to sine cubed. And this method that I'm going to do will work as long as either one of those powers is odd. So what I want to do is split off one power of one of these functions, the one that has an odd power. I want to save that for my du piece, and then I'll let u equal the other function, and then you'll see what happens. So I want to think of this as the integral of cosine to the sixth times sine squared times sine. So splitting off one power of sine allows me to choose cosine equals u and then take care of that sine with the du. Leaving an even power of sine over here allows me to convert the sines into cosines. And the way that I'm going to do that is to use the good old trig identity, the Pythagorean trig identity, cosine squared plus sine squared equals 1. If I solve this equation for sine squared by subtracting cosine squared from both sides, this sine squared becomes 1 minus cosine squared. And now if I choose u equals cosine, like before, then I've got u to the 6th times 1 minus u squared. So all of that is written in terms of u. Then I've got this sine of x that I know will cancel out once I solve for dx. So I'll go through the process again over here. Take the derivative, solve for dx. Plug that in for the dx here. Then these signs cancel, so there are no x's left. That's what allows me to go ahead and move forward with the antiderivative. This becomes u to the 6th minus u to the 8th when I multiply this out. There's another negative that I'm going to distribute into that. So this becomes the integral of u to the 8th minus u to the 6th times du. And find the antiderivative and plug back in what u was. Just using the power rule again. Go back and substitute. U equals cosine x. And there's our answer. To check this one, I would have to, so after I take the derivative, I may have to do some manipulation using this same equation to see that my answer is the same as cosine to the 6th times sine cubed when I take the derivative. But this is correct. You can use this same method with powers of tangent and secant as well, because if you divide both sides of this equation by cosine squared, you get 1 plus tangent squared equals secant squared. You probably remember that equation from trigonometry. This allows you to do something similar to what we did here if you had something like tangent to the 6th times secant cubed. There's also one for powers of cotangent and cosecant, as you might guess.